Hello, welcome to another lesson on Make Science Easy. Today we're looking at how to plan investigations. This is one of the really important things in scientific literacy. Planning investigations is really important because taking part in investigations and doing practical work and experimentation is all part of the scientific method. A good plan is perhaps the most important thing that any practical work or any experiment needs. Without a good plan, you cannot really do any practical work. You cannot hope to get any good answers. So, a scientific investigation should include the following things. An aim. This is the question that you are trying to answer. We need to have a hypothesis, what we think is going to happen and why we think it is going to happen. We need an apparatus list. What apparatus are we going to use? How are we going to use it? We need a risk assessment. Before we do any practical work, we must make sure that we are safe. There is no point in doing experiments if we're not safe. And finally, we need a method. What are we going to do? How are we going to do it? What procedures are we going to use to answer our aim to see if our hypothesis is correct or incorrect? If all of these things are included in an investigation and it follows a scientific method, there's a pretty good chance it's going to be a good investigation. So, all experiments need an aim. They all need to be asking something. It's what this experiment is trying to find out. It's normally phrased as a statement or a question. An aim must be something that can be investigated and it must be linked to a hypothesis. Also, the wording of any aim should be neutral. So what we mean by this is, the aim might be to investigate how increasing the concentration of acid affects the rate of reaction between magnesium and acid. It's a neutral statement. It isn't leading us on. Another example might be to prove that increasing the concentration of acid increases the rate of reaction between magnesium and acid. Now, the first example is neutral. It's a good example. The second one is not neutral. It's already drawing conclusions. It's already telling you what it wants to find out. An aim is just a question. There should be no hint of an answer in our aim. The hypothesis is a statement about what we think is going to happen in any investigation and why we expect it to happen. The outcome of any hypothesis should be definite. We should use clear language. There should be no ambiguity about what we think is going to happen. We shouldn't confuse a hypothesis with a prediction. A prediction infers it's a guess and cannot be tested. A hypothesis can always be tested. Now, before we make a hypothesis, before we say what we think is going to happen, it's generally a good idea to read up on the literature, read up on other experiments that people have done. Make sure you understand the key science behind it, that you look at trends and patterns that other people have found, and then you use that to draw your own hypothesis. Your hypothesis should be based on known information, not making new information up. You can also do preliminary investigations before you make your hypothesis. That means you do one or two very simple and quick experiments to check certain things so you can then build your hypothesis on data. A good hypothesis is generally written like this. If the concentration of acid increases, the rate of reaction between the magnesium and the acid will increase due to the increased amount of acid particles increasing the rate of collision between the acid and the magnesium. It is saying for definite what will happen, not it might happen or it could happen, what will happen, and a definite reason is given to why it will happen. All experiments have variables. Variables are things that can be measured or changed or kept the same in an experiment. So, you must identify these before you start planning. The dependent variable is the outcome that you are measuring. Generally, you will only have one of these. An independent variable is the factor that you are changing in your experiment. And control variables are factors that are being kept the same. So, there can only ever be one independent variable. You can only ever change one thing in an experiment at a time. If you change more than one thing, so X or Y, you don't know if it's X or Y that has had the impact and given you the outcome. So you only ever change one thing. It allows you to draw clear conclusions to link to your hypothesis. Control variables must be kept the same. So anything that is not an independent variable or a dependent variable must be kept the same in your experiment. Keeping factors the same makes sure that it is a fair test, because all of the conditions are the same. The only thing that can cause a difference in your results is a change to your independent variable. All variables other than the independent variable and the dependent variable, by definition, must be control variables. You also need to make sure that when you're designing your experiment, you select the correct apparatus, the correct equipment. If you select good equipment, you will have a good experiment. Generally, you want to choose apparatus that has a high degree of accuracy that measures in a suitable scale. So say you're measuring 5 milliliters of acid, you are not going to choose a measuring cylinder that measures up to 200 milliliters because the scale is going to be no good. You may choose a small measuring cylinder, or maybe a volumetric pipette, or maybe a burette, but a suitable piece of equipment that's accurate and has a good scale for the units you are using. And you need to make sure that you know how to use the equipment before you start. There is no point in choosing equipment that you do not know how to use. You must investigate how to use it before you start. If you don't know how to use it, the chances are it will be used incorrectly and you will get bad results. Measuring volume is one of the most common things that we measure. It could be volume of any liquid, or it could in some cases be a volume of a gas. We need to make sure the size of the measuring container is similar to the volume required. There's no point in using a 5 milliliter measuring cylinder if you need a total of 200 milliliters, because measuring it out 20 times or 40 times or whatever it is not going to be useful. Likewise, if we only need 10 milliliters, there's no point in having a litre measuring cylinder because it's just not going to be accurate enough. Measuring cylinders, on the whole, are useful for large volumes, so when precision isn't necessary. So more than 25 centimeters cubed or 25 milliliters generally. Pipettes are much more accurate than a measuring cylinder, and they're good for fixed quantities when we know how much volume we need before we start. We generally wouldn't use a pipette for more than 25 centimeters cubed. And our final piece of equipment for measuring volume is a burette. These are generally good when we do not know before the experiment starts how much volume we need, because the burette will measure the volume that we use. So each type of equipment has a different use. We need to make sure the correct one is selected whenever they're being used. Now, gases can also be measured, and we use a special type of syringe called a gas syringe. These will collect gas because they have a very, very low amount of friction. So gas will push the syringe out and you can measure how much gas is being released. If you don't have a gas syringe, you can collect non-soluble gases using some very, very simple equipment. You can just have an upturned test tube with a gradated scale or a measuring cylinder in a bowl of water. Water will fill the test tube the whole way up. Any gas produced will displace the water and the water level will go down, and you can measure the amount of gas produced. Just be careful of using this method, because if you have a water-soluble gas, some of the gas will dissolve in the water and you will not get as good a reading. Other things that are commonly measured are mass and time and temperature. Thermometers are used for measuring temperature. You must use a thermometer with a Celsius scale, or in some cases a Kelvin scale, never ever Fahrenheit. It's not a standard unit. Thermometers should be accurate to at least 1 degree Celsius. If you need increased accuracy, things like data probes can be useful. Your thermometer needs to have an appropriate maximum and minimum value. There's no good in using a thermometer that has a lowest value of minus 10 degrees Celsius if you need to record down to minus 30. Likewise, if your highest temperature you're going to record is maybe 20 degrees Celsius, having a thermometer that goes to 150 degrees is not going to be useful. The contents of your thermometer is also going to be important. They can either be filled with mercury or alcohol. Unless you need a mercury thermometer for a specific reason, alcohol thermometers are often preferable because alcohol is less toxic. If you break a mercury thermometer, you can have problems. You should also think about the length of a thermometer. Is it going to be balancing in a beaker? If so, a shorter thermometer might be useful. Are you going to need more accurate measurements? In which case, a longer thermometer might be more useful. So depending on the circumstances, the type of thermometer will be different. And as I've already said, you could use a data probe if you need real precise readings. Now, if we want to measure time, we're going to be using a stopwatch. Most stopwatches or timers are accurate to 1/100th of a second. This is a good level of accuracy because you as a person are probably not going to be any more accurate than that. Mass should be measured with a digital balance. A digital balance is basically a scale. Again, a good measurement, a good level of accuracy is to 1/100th of a gram. And a good scale should be able to tare or zero. This means you put a mass onto the scale, you press the tare button and it will read 0. This is very good if you need to add 2 or 3 different substances to the same beaker because you can then zero it and add the correct amount each time. Every experiment needs a risk assessment. This means before you start, any risk is identified and mitigated. Mitigated basically means reduced. If there are 2 techniques but one is safer, you should always use the safer technique. And an easy way to perform a risk assessment is to put it in a table. So here, I just included one risk, the use of hydrochloric acid. The description of the risk, why it's dangerous. So solutions that are too concentrated are corrosive. The less concentrated the solution, the less dangerous. A more concentrated solution can cause burns or damage to the eye. So this informs us of what precautions we should take. Keep the concentration low. Wear safety glasses. Replace the lid of the bottle when not using it. This will reduce spillage. Clean up any spillage. Wash hands afterwards. All very simple things, but it's making sure that when we do the experiment, we are thinking about these things and we are keeping ourselves safe. When you use chemicals, or in fact, other equipment sometimes, you will see hazard symbols. Hazard symbols are warnings that you must pay attention to. A hazard symbol telling you about a danger will always appear on a yellow or orange background. An instruction symbol, a symbol telling you you must do something, will always appear on a blue background. So here are some examples. Harmful or irritant, not particularly dangerous. Sometimes will have an H or an I. Corrosive. Corrosive substances can eat through your skin, can damage things. Toxic. If you consume too much of this, if you get it onto your skin, if you breathe it in, it can be fatal. Flammable. Things that are likely to set on fire. Oxidizing agents. Fairly similar to flammable things, but oxidizing agents might set other things on fire. Ionizing radiation. This is radiation that, if you're exposed to too much of it, could cause you to get cancer. Quite dangerous. A biohazard. This could be if we have things like microbes. If they are inhaled, if they're released into the atmosphere, they can make you very, very ill. So things to be avoided. Explosive, fairly obvious. It could explode. We want to avoid explosions. So, 3 more symbols we need to be aware about. Laser, this is referring to light. If this light gets in your eye, it's going to be very, very dangerous, perhaps cause damage. Environmental hazard or hazardous to aquatic life. This will generally tell you do not let this get out into the environment. Do not put it down a sink. It's going to cause damage. And an example of an information or an instruction warning, in this case wear eye protection. You'll often see things like wear gloves, and they're fairly self-explanatory. So, we've got our aim, we've got a hypothesis, we've done a risk assessment. We need a method as well. The method is the instruction that we are going to follow. Methods should generally be written in simple step-by-step instructions. One point I need to point out here is this is true for a plan, when you are actually informing yourself or others what to do. If you are writing a report about what you have done, your method should not necessarily be step by step. You should outline all of your variables, your dependent, your independent, and your control. You need to explain how you are going to control your control variables. You may need to give units. So if, for example, volume of acid is a control variable, you wouldn't just state, I'm going to keep the volume of acid the same. You would state how much acid you are going to use. So in every experiment, I'm going to use 5 centimeters cubed of acid. Therefore, anyone else can do this experiment and follow exactly the same way as you have done it. You need to explain how the independent variable will be changed and by how much. You need to explain how you will measure the dependent variable. You should also make your method impersonal, so don't use things like we did this, or I did this, or you did that. Just make general impersonal statements. You must also have a full equipment list, and you may need to include a diagram, and you may need, in fact you definitely need, to state the concentrations of any chemicals used. This is important because anyone who follows you needs to do the experiment the same way. So if you're using 1 molar acid and you don't state that, someone else may do the experiment using 2 molar acid. They may get a different outcome. Your method should also be repeatable by anyone else who's reading it, and if you followed the steps I've outlined, it will be. Finally, any non-essential information that's not required to do the experiment, should be omitted. It should be left out. So, in summary, your plan must be complete for all investigations before you start. You must have an aim, a hypothesis, an apparatus list, a risk assessment, and a method. You must identify your control, dependent, and independent variables, and your method must be clear, concise, and easy to follow by others. So, if you do all these things, I can absolutely guarantee you will make a fantastic plan for any experiment you do. I hope this has been useful. I hope I've made science easy. Until the next time, keep learning.